Да, ну, so today we can finish the proof of the theorem on conjugacy of maximal tori. So let me recall what we were doing. Yeah, so so now, so far we have, let me recall the following proposition, that if the set, so G is connected algebraic, then the following is equivalent. So algebraic solvable for simplicity. So equivalent that first of all that GS is the set of semi-simple elements form the subgroup. And G is equal, and G is nilpotent. So nilpotent means that the corresponding series that differ from commutant series as follows. So just here you have only, so here you apply the commutator to the whole G and then to GI, to the previous commutator as, and this should just for big N, for large N. So you have Gn is equal to identity. So GS form the subgroup, G is nilpotent, and in these cases, just G is the direct product, so the direct product of two groups. So semi-simple part, so this is commutative algebraic actually. Algebraic. And so the product is direct. Yeah? So this, and here, of course, the conjugacy of maximal tori are evident because torus consists of semi-simple elements, so it should be here. So GS is just the maximal torus, so the product is direct. Note that GU is could be non-commutative, of course. So it can be non-commutative. And then we want to establish the general case, so the theorem on conjugacy of tori, so that G is connected solvable. Then just maximal tori are conjugate. And there exists a maximal torus of dimension just equal to dimension of G mod GU. Yes, so in when U is solvable, the set of unipotent elements form the group. So when G is solvable, GU is the subgroup. So otherwise it is not true. So is the set of unipotent elements. It is It is the intersection of G and the set of unit triangular matrices when.
Separate proposition.
Yeah, so this is.
Means that the unipotent elements form a subgroup.
No. If G is solvable, then yeah.
Is it so that all the maximal tori have the same dimension?
Yes, yeah, because they're conjugated. Conjugation doesn't. I mean, a posteriori, if we prove this theorem, then they will have the same dimension. So, but here there is additional property, I mean, which is quite important, that a priori, I mean, existence of maximal torus is not a problem, because a priori maximal torus can be empty. Yeah, so it can be unit group. So the maximal torus is just the map from just the possible homomorphisms of GM in some power injections to your group G. But of course, maximal tora exists. Yes, so because, but what is non-trivial that they are conjugated, and then it follows that they have the same dimension. So.
Did we prove in previous lectures that the connected solvable group? So we have proved already that the maximal tori is a conjugate, but we didn't prove that the dimension.
No. We proved so this was proved, and for this we have out of some fact we derived the existence of tori T in G such that dimension of G modulo GU is equal to dimension of this torus. So we have proved the splitting modulo some special fact that I reserved to be proved a little bit later. And first I want to derive all the try to derive all the consequences, because that fact is related with Lie algebras. And what we have stopped at which point, so we wanted to say that, so it was additional proposition. So notice that I have denoted by G infinity Gn for large n. Yeah, so notice that it is possible to denote this group for, I mean, it is when n is sufficiently big. This holds for the following property, that in the group you have the corresponding sequence of closed subsets. So this n's form the closed subsets. So decreasing sequence of closed subsets.
I see here that we have proved that if G is a fine algebraic, our algebraically closed field, then the maximal tori are conjugate. Is it related to our case? I mean, proved like a similar theorem.
No, if you speak about the theorem that we proved long ago, we have derived that maximal tori are conjugated for arbitrary group using this fact, that for solvable they are conjugated. We have derived out of this. Yeah? So the main point of the proof is precisely this, this proposition and this theorem that we're going to finish today. So yeah, and we'll notice that this notation is well defined for the following reasons. So Gn is the decreasing sequence of closed subgroups, and this corresponds to increasing sequence of ideals. So this stabilizes by Noetherian property. Yeah? But of course, the special case, I mean, that the group is solvable, that it is a more special thing that it stabilizes precisely at, so the group is nilpotent, is that it stabilizes precisely at the unit element. So I want to prove the following, so why we have introduced this notation, I want to prove the following proposition that if you have just S will be a semi-simple element, then I claim that it can be conjugated. So there exists an element U inside the G infinity such that U S U inverse, so S is conjugated in this in our fixed torus. Yeah? So then, so let us derive this. And also I shall need the following remark. So if of course, if it is algebraic, connected and solvable. So and if you want to have the following, this conjugacy works of course only over K is equal to K bar for algebraically closed field. It is quite important because otherwise you can easily give two examples of tori. So like in SL and C there is just the torus like this and the torus like cosine, well, better to say A, B, A minus B, where A square plus B square is equal to 1. Yeah, so it is the same as writing here cosine phi and here sine phi, but for algebraic language this doesn't make sense because these are not algebraic functions. Yeah? So of toruses that are not conjugated over R, yeah, so not conjugated. So they both has dimension 1, yeah, but not conjugated over R. So these are subsets in SL2C that are not conjugated over R. No, it is because the field is not algebraically closed. I mean, for any, so we have the, yeah, so maybe I should say it as the remark. So this theorem, so main theorem for today implies that for K equal to K bar, just maximal tori in any G algebraic and affine group are conjugated. If you wish to recall this, this is simply because, yes, so who can help me to recall this?
Because we can put
yeah, so the tori, yeah, so if you have two tori, without a loss of generality, you can find conjugations. So if you have two tori S and T, you can conjugate them by two elements and two different elements. So they can be put, they are both solvable. So since they are connected and solvable, then the theorem for solvable groups tells you that any connected solvable group can be conjugated in a way that it is subset in a fixed Borel subgroup. So without a loss of generality, you may put them simultaneously in the same group. So, and this will be solvable, so we simply apply this theorem. And so this theorem is, so also we need to recall the following fact, that since if G solvables and connected, then we have derived that GU is connected. And also we have derived that commutant. Yeah, so you triangularize, so the commutant sits inside the commutant of two triangular matrices. But this is just a unipotent subgroup. So the commutant always sits in the unipotent subgroup. So it is automatically nilpotent. Yes, so then G times G is nilpotent. And also notice that G infinity, it is just, well, many applications of commutants. So here it sits G infinity. So G infinity is nilpotent that we shall use today. So since, so now we shall prove the proposition. So actually I have almost proved it on the last class, but it was sketchy. Besides, there was some kind of, so we were a little bit stuck because of the order of the elements written. So as for the proof of the proposition, it goes in the following lines. So notice that so first of all, the group is not nilpotent. Yes, so that we may assume that G is not nilpotent. So the G infinity is not trivial, and then you know that G infinity is nilpotent itself and connected, so of non-trivial dimension. This implies that if you start looking at the factors, corresponding factors, so just put it just G tilde. So if you look at the corresponding factors of the form, so last one will be trivial. So you see that the previous factor has positive dimension, and it is central, yeah, because you have for this the commutant with the whole GT, it is just 1, yeah? So that means that G tilde n minus 1 sits in the center. So this implies that the center is non-trivial, yeah? So this the connected, moreover, the connected component of the center is non-trivial. So we may assume this, yeah? So just put n to be the connected component of G infinity. So notice now that yeah, you have this element S. Yeah. So what can be said about this element? So S normalizes G infinity. Yeah. So because it is written in terms of commutators. And the group, this in terms of commutants, and then it can be written in terms of products of commutators. So G normalizes G infinity, and then it normalizes all the objects that are defined via some relations. So then S normalizes the center. Explain this.
So G infinity is nilpotent and connected?
Yes. So then I have derived that this thing. Yeah?
Okay.
So that the center of G infinity is, so if the group is nilpotent and connected, then I claim that the connected component of the center is non-trivial, so it has the positive dimension. Why? Just because if you have the factor which has which is unit, so on the previous step you have the thing that doesn't coincide with the unit. But it can happen, so how it can happen? That the thing has either larger dimension or several components, or it is just finite collection of elements which is which contains unit. But the latter is not possible because this is connected. So that means that it is not finite collection of elements, then its dimension is positive. So this implies, yeah, so this, since I can write this, so this is, so if, yeah, so if this, so just if G tilde is not zero, so not identity, so there are two options. It is finite collection of points, which of the quantity more than one, or it is just dimension is bigger than zero, but it is connected, so it is connected. So this is not possible. And but the last equality, so that this is just definition of Gn minus 1, that this is trivial, tells you that this group sits in the center, and in particular, the center can be disconnected. But even if it is disconnected, it has dimension larger than 0, then because it contains the group of non-trivial dimension. Yes, so the dimension of the center is bigger than 0. So this implies that in particular connected component is not. So yeah, so we are more or less on the step that we have finished. So, but you have this element, so you want to reduce everything to this case. So notice that so everything here is normalized, so we can consider normalized by S, and S normalize this also the connected component. So then you just get the following, that S is yeah, so you have this natural projection. Yeah? So this is yeah. So just yeah, I wanted to say that the following: that any element, so any element of G normalizes G infinity. Actually, any automorphism of G maps G infinity to itself, but this won't be used here. So then it normalizes Z of G infinity, the center of this, and then in the end of the day, G normalizes the connected component. Is it clear? Okay. So this implies that this group is normal. Yeah, so that in particular that n is normal. So actually it is even actually it is even normalized by any automorphism of G, but by any automorphisms of G, but it won't be used here. So it is normal in the strongest sense as it could be. Yeah? So, ну, потому что она, ну, сопряжение ее сохраняет, ну, сопряжение относительно любого элемента. Не, может, я вот это должен вам пояснить? Ну да, почему? Ну потому что как бы если вы, вы можете даже взять любой автоморфизм, да, если у вас есть ряд коммутаторов такой, то если вы навесите на него φ, то будет то же самое. То есть как бы вот этот, поэтому, ну по индукции вы доказываете, что это φ от g и плюс 1. Ну как бы при сюрреактивном морфизме, да, то есть so if phi is surjective. То есть как бы so and if you have the center is defined as follows. So it is just the set of commuting elements. So x belongs to G. So if you apply any automorphism, then phi of G will be phi of x will be phi of x, phi of G. So this can be put to be any element since phi is again surjective. Yeah, so here you can express it that it happens for any G tilde. Yeah, so if you write down any element G tilde as phi of G, this will be computational a relation that will be preserved. And if you take the connected component, the automorphism of variety maps unit and the unit and connected component to some connected component. So it leaves connected component.
Is it so that if an element lies in G infinity, which means that it commutes with all the elements of G infinity, then every element of G leaves this element on its place?
Yes. Нет, он его не оставляет на месте, он его переводит в элемент с теми же свойствами. So it doesn't leave it fixed. It maps to the element with the same properties. So, and the same for connected component, because if you apply phi of connected component sits in some connected component, coincides with some connected component. Well, it sits in some connected component, and the inverse just makes it related with the previous one, and phi of identity is equal to identity. Yeah? So that's why the component should be component of the unit. So so it can permute the components, but the component of the unit, it will be fixed. And since it is normal, so we can pass to the corresponding quotient. And so for the quotient already you know that we can conjugate our element S by just five, just so there exists X in G infinity modulo n. So this means that it exists the element for G. Notice that under surjective homomorphisms, as we have noted, pi of G infinity, of course, maps to pi of G infinity. Yeah? So just G, which is G mod n infinity. Yeah? So this by induction assumption for G mod n. So there exists X such that pi of X times your element S. So you conjugate by this element, and it belongs to this given, the image of the torus of pi of T. So the image of the maximal torus inside T. And this actually means that if you think of what is pi of T, it is the group generated by T, so it is pre-image. So this, yeah, so here it is pi of S. So this means that if you take the pre-image of these elements, that X as X inverse will be inside pi pre-image of pi of T. So it is kernel of pi times T, which is just T times n. Yes, so also just notice that n is normal, so I prefer to write this down in a different order. So just since n is normal. So, and now, so we have taken the element, so we have conjugated in some smaller subgroup that was a little bit smaller than just arbitrary element in G. But now we have to conjugate this element, already find some element such that in this group n times T, it will be conjugated in T. Yeah, so I want to keep this theorem because I want to use it. Yeah, so this means that there will be, so it is sufficient to find y. Find y that will sit in n, so n is a subset of G infinity, such that X inverse so is conjugated in G infinity. and is conjugated in your given torus. So we again denote this by S for brevity. Yeah? By S for brevity. So we have the following. So we have S that is written as a product of the element n and some element t. And notice, so this is some element of torus, and n is the element of n. And notice that n is normalized by normalized by element of t. Yeah. So and also notice that this implies that let us recall the lemma. So that T is a semi-simple element, and so U is connected unipotent group. And n is actually here, it is commutative, yeah, so it is central, so but in particular it is connected and unipotent. So you have yes. This was already unipotent. Yeah? G infinity was already unipotent. So just we shall put n equal to just u equal to n in this theorem. So we have taken the centralizer of t inside u and times the variety m, and this was a bijective map. So this product, just taking the product of two elements, was proved to be bijective. So let us put, and let us apply this to this t, so we can write down, so let me, I'm not sure that it should be t or t inverse, so, but it can be applied either to t or to t inverse, so let us do it now. So let us take, so
I remember that we had kind of such a lemma, and you wanted
yes.
closest variety of unipotent elements, which is gamma s of u.
Yes. So m is precisely, so m is m. So I forgot to say that m is precisely image of gamma t of u, where where gamma t is just the commutant. Yeah. So gamma t of the element u is just the commutant ut. U inverse T inverse. Yeah? So just apply this to n. So just I'm stating it. So apply this lemma to.
So it is the lemma
that was proved. Yeah. So. And what we shall in this lemma. You should also, there was a remark that we shall probably use today. I mean, probably because it depends on the time. That if, but let us recall it, that if u is commutative, which is actually the case here, yeah, because we have taken the center. Then gamma t is homomorphism. Gamma t is homomorphism. centralizer. Yeah, so the set of elements that commute with all elements of U. So the set, let me put it, that CTU is just the set of elements of U such that U and T commutes. Okay?
So this is the centralizer of an element which lies inside U.
It is, yeah, so it is a subgroup of U. Yeah. So if U is commutative, then gamma T is homomorphism. Yeah, so the gamma T, just xy, is just gamma T of x, gamma T of y. So this is used just explicitly. So let us apply this lemma to n. Yeah, so to the element n. So apply lemma to U equal to n, element T, and express element n. Yeah. So express n. So this means that n can be expressed as the product of the element which lies in the centralizer, Cu of T, in U, and maybe it is better to write like this. So it lies in the centralizer, and then you have to write it down as the image of this commutator map. So it looks like U T U inverse times T inverse. Okay? So, and let us now substitute this inside S. So put S to be n times T, and the order is of particular importance here, because I want T to be cancelled with this T. Okay. So what is written here? So here you have the element of CUT. So and also Z, also Z is the element, in particular it is the element of N, which is the center of G infinity. So this is commutative group. So Z commutes with U and T. So the Z commutes and T, and this implies that Z commute with U T U inverse. So what you have? You have here you have a semi-simple element, and it's not surprising I shall use Jordan decomposition, yeah, because this is unipotent. This is semi-simple. It is conjugation of semi-simple. They commute. So this is Jordan decomposition. So by Jordan decomposition, the unipotent part should be trivial, yeah, because this is semi-simple element.
Is it true that the product, the lemma which we use says that
Не, ну, в смысле, что все, да, что, нет, но вот этот U, он определен не единственным образом, потому что это как раз именно существование, потому что, ну, здесь есть явные элементы, элемент из образа, да, но такие U могут быть не единственные. Ну, то есть, как бы, если U коммутирует с T, ну, если вы U умножите на элемент, который коммутирует с T, он сократится.
То есть, с одной стороны, вот ЦУ это элементы, которые коммутируют с Т, и они в М...
Ну, они в M отображаются тривиально, да, но yes, so notice, so that was, the discussion was about the following. So notice that here in this notation, yes, so this map from CT of U times M is bijective, but the element, the expression of gamma T of U, the element of U as the product of U and T, as the commutate of U of T, it is not unique, yeah, because if you change U by the element which commutes with T, you will get the same element. Yeah? So if you take U times U tilde T, so this will result in the following. So if U tilde commutes with T, then it will be equal to the same commutant. Yeah? So this tells you that, of course, the way to write this down, the element in this form, is not unique, but we just wanted to write it down in this form for the proof. So, what we have so far, this is semi-simple element. This is a product of unipotent and semi-simple. They commute, so by Jordan decomposition, this is Jordan decomposition of semi-simple element. This means that Z is an identity element. And this is precisely what we needed, the element of S. Yeah, so this element S is written as the conjugate of element of T. Yeah, so this means that S is written as U T U inverse. That so just the conjugation of U inverse S U belongs to the torus of T. So which we really wanted here. Okay. Yeah, so there is just some kind of misprint in the Humphreys book, as I understand, that here he uses, so the problem is that he uses different order of these two elements. Yeah, so he's using T times N, and but using the element, so this expression for T inverse, but that actually, but he uses expression written starting from T inverse U T inverse. So here somewhere I had made so from this element he has taken the inverse of this element. So formally there is a misprint, but that doesn't affect, of course, the proof.
What did we prove by showing that
Ну вот это, ну как бы мы просто сделали следующее, мы по индукции нашли элемент, вот я это уже стер вот с этой доски, по индукции мы нашли элемент, который, ну вот у нас был полупростой элемент, мы его хотим сопрячь в максимальный тор, да? Вот, но мы действуем по индукции, применяя его к фактору, мы смогли сопрячь так, чтобы он попал в тор в факторе. Но это равносильно тому, что сопряжение этим элементом, ну каким-то, попало в произведение тора на n. Ну а дальше, ну как бы вот внутри произведения тора на n, мы еще хотим досопрячь так, чтобы этот элемент попал внутрь тора t. То есть мы доказываем, что любой элемент S, который ну, принадлежит произведению n на t, которое на самом деле t на n тоже. Ну, то есть может быть записан вот в таком виде. Может быть сопряжен, что найдется элемент из, ну, что существует элемент из g бесконечности u такой, что он его сопрягает. Ну, да. Да, то есть эта штука лежит в n, а на самом деле, да, она лежит еще и тем самым же бесконечности. Поэтому мы S досопрягли так, что он попал внутрь T. Ну, в принципе, вот то, что... Где? А? Нет, T это вот исходный тор, максимальный тор в G, да. То есть мы как бы сумели первым шагом индукции сопрячь в группу T на n, а внутри этой группы, уже действуя с помощью элемента n, мы досопрягли уже, ну, внутрь самого T. Вот как бы вот этим элементом.
Таким образом мы показали...
Ну, сопрягли наш любой полупростой элемент в данный максимальный тор. Это еще не говорит о сопряженности торов, но сейчас я это выведу. Да, ну у здесь в этой записи принадлежит. Да? Хорошо. Теперь я хочу что-то стереть. Yeah. Because any element of G, so here I have precisely erased this picture. Any element of G, conjugation by any element of G normalizes N. It normalizes G infinity, the center of G infinity, and any conjugation by any element. So let me write it down again. So if you take any element of G, so any element of G, yeah, then G infinity, G inverse sits inside the G infinity. Okay? So actually this, yeah, so now I will explain it. Yeah, so if you allow. So it is convenient to notice that this G infinity G inverse can be viewed as the map from, so you can consider phi as a surjective map. So just consider now arbitrary phi, which is a surjective map. Surjective map. Surjective homomorphism. So it is surjective homomorphism, and in particular you can take phi of S. So for example, phi of x is equal to G x G inverse. Yeah, so you can take this any surjective. So you can take this surjective homomorphism as the given one by G x G inverse. Okay. So the claim is so the claim is of the proposition that phi of Gn sits inside and actually is equal to Hn. And so if phi is any homomorphism, then you have inclusion. And the reason is that phi of if you apply, so this is by induction. Yeah? So by induction, so this is just because phi of Gn can be written as follows. So phi of Gn can be written as phi applied to the commutator with Gn minus 1. Yeah? So this is equal to, so you can put phi inside the commutator because it is homomorphism. So it is phi of g, phi of gn minus 1. So you can change by induction this phi to just and let me prove it just without surjectivity. Yeah, so that if you have any homomorphism, that you have inclusion here. Yeah. So by induction, this sits inside just applying so h n minus 1, and this sits inside h. So everything sits inside the commutator of h and h minus 1, so it is hn. Right? And if you have surjective map, so if phi is surjective, so here you have equality, and here you have equality by induction. Okay, so this will be equality here. So it is just a very general statement. And actually the same for series where you are writing down commutant of this, not with G, but the commutant with, so like this. Yeah, so with this series where you're applying the commutant to I minus 1, commutant to I minus 1. Yeah. So this also holds for such series as well, for the similar results. And for surjective map, there is equality, otherwise it is just inclusion, but here you need actually only inclusion. Yes, so you just that. The thing maps to itself. Yeah, so now I want to erase this one. If you need to something to be explained, please stop me earlier. Just at the place you do not understand it. I mean, it will be much faster for us. So, yeah, so the next step is to prove the conjugacy of maximal torus. This is conjugacy of maximal tori. Yeah, so the idea is to use the following. So suppose you have S and T, you want to understand that they're conjugate. So the idea is to take S. So these are to be maximal tori. So maximal tori. So you do not know that they have, so now we do not know that they have the same dimension. You do not know that they are conjugate. So just the thing is that actually what you need it is just what you need is the following. So S actually will be, so it should be D group. And T is the maximal torus. So I claim, so this D group, it is extension of torus and some finite group. So finite abelian group that can be a priori diagonalized. So then just I claim that there exists the element u from G infinity such that U inverse sits inside T. So how do we prove this? So the idea is the following. So how to reduce this to the previous case? So we had a proposition that for any D group, you have, so there exists an element S. Yeah, so maybe better to say here the torus, I think. So this is, so the torus. So just for the torus, there exists the element of S such that the centralizer of this element in G is equal to the centralizer of the whole torus. Yeah? Okay. So it is a sufficiently general element. So what we have, you can do the following. So now, just by previous step, there exists U such that S can be conjugated, so such as US U inverse sits inside T. You can conjugate this element of T, so without a loss of generality, so without loss of generality, we have the following situation. So you have T. So here you have unrelated torus S. Yeah, so just S is just, so we change S to be US U inverse. Yeah? And you have element S, which is both inside T and inside S. And this element S is just, yeah, so maybe I shall write down like this. So S is just US U inverse, and S tilde is just S U inverse. And what you have, so you have the additional property. So the centralizer of S tilde inside G is equal to the centralizer of S of S biggest tilde in G. Yeah, because these are just conjugated. So this is, they are conjugated to the centralizer of S. Yeah. So this is the conjugated centralizer of S, and this is conjugated centralizer of the torus. Yeah? Okay, and then what does it mean, this kind of picture for us? Yes, so S tilde sits inside torus and inside S tilde. So this implies, yes, so that the torus sits in the center. So since the elements of torus, they commute with each other, so this means that the whole torus sits in the centralizer of S tilde. Yeah? S tilde. And in particular, this is equal to the centralizer of the whole torus, S tilde. And this implies the following, that this torus commute with S tilde. So all elements of T commute with the elements of S tilde. So we may form So we may form the product of so the product of this torus and the torus S tilde, yeah, so that we may form the product of S and T. And this no, just not so notice that they commute, yeah, so that means that you have the homomorphism. So this product is just a group homomorphism. So you have group homomorphism to your group G. So just mapping just a pair of elements to ST. And this means that the image of this, the product of toruses is connected diagonalizable group. So connected diagonalizable group. And it is larger than, so ST contains T, so which is contradicts the minimality, yeah? The maximality of T. So it is connected diagonalizable, so that means this is a torus, but it strictly connects, contains T, so this contradicts minimality, maximality of T. Хорошо? Понятно? Вопрос какой-то, да?
Я не поняла, почему существует один элемент в S.
Ну вот это предложение отдельно, но это мы доказывали, оно следовало просто из прямого вычисления. So there was a question how we proved this proposition. So we explicitly proved this for GLN. So we have proved the following. So if you have this S that sits in GL of V, so we have explicitly calculated the element. So we have written conditions on the element of S. So just such that the centralizer of S will be the centralizer of the torus S. And then we can derive this as just the intersection with, so just intersecting this with G tells you that the centralizer of S of G is equal to the centralizer of big S of G, in G.
So this was proved for a torus inside GLV.
So this, yeah, so this was proved for a torus inside the GLV.
Means that any element in S would satisfy.
No. The problem is the following. So let us recall how it was proved. So there was condition. So V was decomposed into the direct sum of the characters of torus, and the S was taken in the so the V was diagonalized. Yeah. So it was decomposed into the direct sum, and S was taken to be just not belonging to the union of kernels of chi I inside S. So we consider just the kernels of the characters with the maps from S to K star. So you can consider kernels of this map. And if you take the element of the special form which doesn't is not contained in the union of kernels, and this is finite union of hypersurfaces. So finite union of proper subvarieties, yes, of hypersurfaces. And since we assumed that the field is algebraically closed, the complement to such subset has points. So because it can happen that if the field is finite, it is just covered by the finite collection of hypersurfaces. All the elements contained in some finite collection of hypersurfaces. But here you have infinite field, so you can take the element outside this set, and for this you have this kind of problem.
It means that the complement-wise, this S would compute with G, and this means that any element of S would commute with G.
Yes, yes, yes.
Because all that can happen is that an element would go to the kernel higher.
Yeah, so we have written this as the block matrices. You have to recall this calculation. And yeah, so then the idea first to make conjugation such that this element, this special element, will be inside your torus T, and then the idea is to use this property. So notice that for the conjugate element you have the same equality for centralizers, and then the property that you have an element which is contained in the torus T and the S tilde, you get the following. So this torus is commutative, so it contains the centralizer of the element, so it contains the centralizer of S. And this means that T commutes with S tilde. But if T commutes with S tilde, you can form the subgroup just generated by the products, and it will be homomorphism of this product, which is a abelian group, to G, just because they commute. Yes? So this product map, simply product map, is homomorphism. So since S tilde and the T commute, this phi is homomorphism, and this implies that this is an image of diagonalizable group, so image of maximal torus of D group, and we have so it is connected diagonalizable group, which is torus as we proved it. Yeah? So it is, since it is connected diagonalizable group. So just if the torus, so we have enlarged the torus by the product, and which is not possible because of the maximality. Okay. So now just let me derive some property corollaries out of this. And so just ну давайте сделаем вот сейчас тогда перерыв. Сейчас самое время. Ну что, давайте продолжим все-таки. So, I wanted to discuss now several properties. So notice that in particular, if here we shall discuss Cartan subgroups. Yes, so Cartan subgroups and density results. Density. So Cartan subgroup now is defined as follows. So you take T maximal torus, and C of T, the Cartan subgroup related with T, so is defined as the normalizer of some maximal, the connected component of the centralizer in G of some maximal torus. So connected component of centralizer. Actually, it is also connected component of normalizer, as we have proved. So, so in particular, what you have, so notice that it is nilpotent. So, so property. So all such subgroups are called Cartan subgroups. Yeah, so just definition. Yeah, so those that are centralizers of maximal torus. In particular, so just since maximal tori are conjugated, since maximal tori are conjugated, so again, I consider it over algebraically closed field.
All the elements of commute with the torus elements.
Yes. Yeah. So in particular, the centralizers also are conjugated. So this means that Cartan subgroups are also conjugated. So C of T are conjugated. Then C of T are conjugated. So Cartan subgroups are conjugated. So Cartan subgroups are conjugated. So notice that let me notice that if you have so what about this centralizer? So what you know about this centralizer, that on one hand, so the centralizer contains a unique maximal torus. Yeah, so otherwise, yeah, so we have the following. So we have two toruses. So one is T and one is S. And so by previous theorem, by previous theorem, it is they are conjugated. Yeah, so this implies that they are conjugated as just that S you are conjugating it by so T can be conjugated inside S, but for element of so you are thinking it as the torus is inside the centralizer itself. So you apply the theorem of conjugacy to C of T. So this implies that you can conjugate the torus inside S and by the element of C of T. And but such G fixes T. Yeah, so that GT G inverse is equal to T, so we get contradiction. So you have only one maximal torus inside your group. So this implies that the set
Is it Cartan
no, it can be just a product of non-commutative semi-simple part and some non-commutative unipotent group. Нет, если иногда просто, ну как бы, иногда картановскими подгруппами, то есть то, что вас может смущать, иногда люди картановскими подгруппами называют просто сами максимальные торы по причине того, что в редуктивных группах картановские группы и максимальные торы совпадают. Но вообще говоря, если вы ее определяете вот так, то она может быть, вы можете взять прямое произведение вот полупростой части унипотентной, и это будет, ну, вы можете взять тор внутри вот этого дела, и, ну, как бы, so there is evident example, just take T and multiply it by any unipotent group, or just as you can take a direct product, so take here the torus T. Then trivially this GU will be centralizer of T, but GU is non-commutative. So you will get that this will be precisely the case. So, and notice that notice that since the set of semi-simple elements form the group, so since G, so we know that now we know that given any semi-simple element, so if you take any semi-simple element, then S just is conjugated to the element of maximal torus, but U for U that belongs to the centralizer, but you commute with the elements of torus, so this implies, this implies that S belongs to T. So any semi-simple element is belongs to the torus. So that means that all elements, semi-simple elements, coincide with the torus, and thus you get that so that means that just if notice that if you take now the just arbitrary element, so just arbitrary unipotent element u in CGT unipotent element, so just I claim that if you have two unipotent elements, they are also their product is unipotent. Yes, so that means that U1 and U2 is unipotent, and this is due to the fact that just if it is not unipotent, is just written as U tilde times T. Then, for example, you can move this element here. Yeah, so just yeah, so yeah, so just yeah, so actually we have already proved that if the semi-simple elements form the group, so that if GS form the group, then the group is nilpotent. Yes, so then G is nilpotent. So this is a direct product of GS times GU. So so this implies that the Cartan subgroup is automatically nilpotent. And actually, so the problem that is given for the class is that this group can be characterized as follows. So C is a Cartan subgroup. If it is just if it has two properties that just so if it is C is connected, nilpotent, and C coincide with its normalizer in G, with connected component of its normalizer. So yes, and G of C, yeah, the normalizer of itself. So this is the claim. So now I want to derive the following. So now we had just now I want to prove the following fact, that actually any element can be put in which is interesting, just interesting theorem on its own, that just given GS and GU are semi-simple and unipotent element, then GS sits in T for some maximal torus, a unipotent element sits in the unipotent radical of the Borel subgroup, and the arbitrary element G can also be put in the just G belongs to B tilde for some Borel subgroup. So this is so far we have learned how to take the connected solvable subgroup and put it in the maximal connected solvable subgroup, which is Borel subgroup. And here the situation is more tricky. So it tells you that just the semi-simple element can be conjugate to maximal torus. Any unipotent element sits in unipotent radical of some Borel subgroup, and arbitrary element can be put in the Borel subgroup. And the problem is
Conjugated to be placed.
yes, yes. I mean I do not fix BT and B tilde, yeah, so that I'm just saying that they sit in some of the conjugated subgroup. So you have the following story. You have in the group G, you have sets of maximal tori, Cartan subgroups, and Borel subgroups. And all of these objects are just, so the elements in the sets form, so they are conjugated between just, so you can take any representative of the set after, if you are allowed to make a conjugation. So, ну, то есть у вас есть внутри группы G есть множество максимальных торов, множество их связанных компонент-централизаторов, то есть картановских подгруппы и борелевские подгруппы. Ну, и в каждом множестве, то есть торы сопряжены, борелевские сопряжены, картановские сопряжены.
Но GS мог не лежать в торе до того, как...
Нет, ну я же сказал для некоторого тора.
То есть,
ну, то есть, что найдется тор...
Каждый S проходит по максимальному...
Да, но вы не знаете, да, какой тор. Да. Не конкретный, да.
ЖУ проходит по борелевской.
Унипотентный радикал борелевский, да.
И даже через каждый G проходит борелевская.
Да. Но на самом деле, so this follows from, but in fact, yeah, so this we actually proved, but this follows from more general fact. So this follows from that there exists a Cartan subgroup containing this element G. So actually the set of conjugates of, so notice that if you start conjugating the maximal torus, it doesn't cover a whole group G. Yeah. So all conjugates doesn't cover the whole group G. Yeah, so in general, just because it can happen that you have unipotent elements that doesn't belong to maximal tori. So again, clearly, G is not equal to the set of conjugation of the unipotent subgroup. So U is radical the set of unipotent elements of B. So set of unipotent elements in B, which is Borel. Yes, so which is a Borel subgroup. But in the same time, if you take the Cartan subgroups, which has the property that чего-то я не то говорю. Секунду. Не, про борелевский это верно, а про картановский это как-то что-то... это... Не, все, yeah, so the... Yeah, sorry. Yeah, so, and, yeah, so, and for, just, so, and... yeah, so, and also, yeah, so this is not true for Cartan subgroup, but, yeah, but what is important here? So this, so it can happen that these sets are not everything, yeah, so they're not only not all the group, but their closures is also not the whole group, yeah? То есть, как бы вот, ну, если вы начнете сопрягать полупростые элементы, ну, в смысле, максимальная тория унипотентная группа, то вы не обязательно получите всю группу G. Это по очевидным причинам, потому что здесь все элементы унипотентны в этом множестве, здесь все элементы полупростые, да? А у вас бывает, что есть непотентный элемент или не полупростой. Но также еще замыкание вот этого дела и замыкание вот этого дела может тоже не совпадать со всей группой. Ну, потому что у вас может быть просто вот как ситуация здесь, прямое произведение полупростой и унипотентный, да, ну, как бы, что все унипотентные лежат здесь, все полупростые здесь. Поэтому, что бы вы ни делали, вот это множество, оно лежит здесь, а вот это множество, оно лежит здесь. И их замыкание тоже. Вот, но как бы, so if you take the Cartan subgroup, then the conjugation of, so this will hold from the following proposition, follow from the following proposition, that the set of conjugations of Cartan subgroups, the closure coincide with G. Okay. То есть, ну, как бы, что вот это свойство, оно выполнено будет для картановских подгрупп. But in the same time, what we have proved that so we have proved that also, yeah. So notice that how to derive this proposition. So assume that this is true. So let us derive. So proposition 1. Proposition 2. So let us derive 2 implies 1. So also we have proved the closeness theorem. So if B is Borel subgroup, or the group P contains Borel, then the set of all, so the set X, which is the union of all conjugates of GP, is a closed subset of X, of G. Okay. So what does it mean for us? Yeah? Нет, мы доказали, что для любой P, ну, для любой P, содержащих борелевскую, их нот объединения сопряженных будет замкнутым под множеством G. Ну, на самом деле мы доказали следующее, что мы доказали более общий факт, но давайте я его вспомню. So we actually proved the more general fact that was the following. So if you have Y inside X, so this is G variety, and this is closed B invariant variety, variety, then the G span of Y, yes, so then, that means that just By sits inside Y. Then G span of Y is closed in X, is closed subvariety of X. So here, of course, I mean that G acts on X, so on X algebraically. So if you have, so this is a general lemma that says that if G acts on a variety, you have the subvariety which is B invariant. Then if you take G span of this, then this will be invariant. And this is trivially applied to this situation because P, if P contains B, then G, well, B, P. So the action is just action. So X is equal to BG. So Y is equal to P here. And G acts by conjugations. So if P contains B, then of course it sits inside B, so this condition is satisfied. So you take the union of all G of conjugates of P, so this is closed. Yeah? That was the lamp. Ну, пусть, давайте рассмотрим такую лемму. Пусть G действует на многообразии X, и пусть есть некоторое замкнутое подмногообразие, которое B-инвариантно. То есть, ну, вы действуете на нем любым элементом B, и оно попадает в себя. Тогда утверждается, что если вы разнесете Y с помощью элементов G, ну, то есть рассмотрите объединение G, подействовавшее на Y, то тогда это многообразие будет, ну, оно же инвариантное и замкнутое. Но такое неочевидное следствие. Ну, в смысле, неочевидное утверждение.
То есть то, что G инвариантное, это...
Но это очевидно, потому что вы взяли все элементы G, подействованные на Y. А то, что оно замкнуто, это не очевидно и следует из того, что G фактор по B полное. Ну, как бы вот. Ну вот, а вот эта часть, ну, как бы я просто применил непосредственно, но если вы берете P подгруппу, содержащую B, а действие X это все G, Y это P, а G действует сопряжениями, что BP минус 1 лежит в P, ну и объединение всех таких групп, оно замкнуто.
Почему B полный?
Нет, G фактор по B, P полное. Ну, потому что оно проективное, это замкнуто в проективном. Но мы это показали, как бы это. Это была отдельная, да, теорема.
G действует на X, но G действует на X, но в G есть подгруппа B, что G по B полный.
Нет, B это барелевская, B это барелевская. Это, да, B это барелевская подгруппа. То есть как бы это вот такое свойство барелевских подгрупп важное. Yeah, so, but C is nilpotent, C is connected and nilpotent.
Правда, что как-то алгебраические группы потом по подгруппе, которая является полным многообразием?
Нет, не B полная. Подгруппа не может быть, ну, в афинной группе подгруппа не может быть полным многообразием. Нет, это именно G фактор по B полное многообразие. Потому что мы его реализовали как замкнутую орбиту многообразия флагов. Если.
И то есть здесь B могла бы быть любая группа такая, что G по ней.
Да, но это свойство как раз, ну вот оно характеризующее свойство. Что это для, если G по P полная, то эта группа содержит B. Поэтому оно не, ну, ничего не меняет здесь, ну, как бы в этом утверждении. Ну, не улучшает. То есть, написав там P, вы не, ну, как бы ничего не улучшите. So, if G is connected and nilpotent, then C is contained in some Borel subgroup. So it is solvable. And so C is contained in B for some Borel subgroup. Just in some Borel subgroup. So you use the following statement. So you just by proposition 2, you have the G coincides with the closure. But in the same time, the union of G sits inside the union of Borel subgroups, conjugates of Borel subgroups. And this is already closed. Yeah, so this is closed. So of course, the closure contains. So this contains the closure. So this means that. This means that G is just is equal to the closure. This closure contains this one, but this is equal to the union of all elements of G without taking the closure. So that means that they coincide. Yes, so you have equality here. So this means that any element can be conjugated inside the B. So just any element can be conjugated to the element of B. And this implies also that So that if you take unipotent element, so if G is unipotent, so if G tilde is, if GU is unipotent, it is, GU is conjugated to the set of unipotent elements, so which are precisely the element in the set of unipotent elements of B. So in U, all unipotent elements of B. So, and how we derived the density theorem. Yeah, so now we have to check the conditions of density theorem. Да.
Why does the proposition that the union of GBG minus 1 is closed leads us to that every element can...
Не, ну смотрите, все элементы G получаются как замыкание сопряжения вот этого. Но вот это лежит вот в этом, да. А C лежит в B, значит вот это лежит в этом. Но это уже замкнутое подмножество.
А вот этот C это...
Картановское. Ну, картановская подалгебра. То есть утверждается, что ну, для Е... Что...
Просто
Да.
мы пользуемся там, вот этой левой справа.
Да, да, да.
Картановская лежит
Да.
в B, а B замкнутая, значит...
Не, в смысле, вот это замкнутое, ну, значит, G уже совпадает с этим.
А почему же это замыкание сопряжения первого?
Это вот сейчас я хотел показать. Ну, в смысле, это вот это предложение. Yeah, so the proof of proposition 2. We had the following density theorem, so it was proved separately. So actually this theorem is called closedness theorem, and this kind of statements are called the densities theorem. So here you have any subgroup. So you consider the union, so the union of G. So if there exists an element, yeah, so yeah, so if there exists an element T such that the element of the Cartan subgroup.
The density theorem is just the theorem that will help to prove.
Yeah, so that we will help to prove proposition 2. Yeah, so this is exactly the statement that says what is, by which conditions we need that in order to guarantee that this thing is dense. So suppose you have the group so such that there exists an element such that with the property that the set of fixed points of T, the set of the just fixed points for the action of T on on G mod H is finite. So suppose you have this property. So suppose you have in H you have very special element that so you have a natural action that T maps the coset to the coset. Just T maps the coset into TXH. And suppose the set of such X is finite. Yeah, so the fixed cosets by this section of T is finite. So then I claim that G is equal to the closure of this set. So this we proved. Yeah. So that was. And now the claim is that there exists such element in the Cartan subgroup. Yeah, the closure. Yeah. So that was obtained by the just there was a map. Yeah, so that the map just simply there was a map from G mod H to times H to G. Yeah, so that take the coset and take the element and acts by the representative of this coset on the element. I mean, this is not a well-defined action, but this is well-defined map of the variety. It is just so this can be viewed as some map of the varieties, and this map, yeah. So if you and we have calculated more or less the dimensions of the fiber of this map, and we proved that this map is surjective. Yeah. So yeah. So actually, I mean that there is this map, but we have calculated the dimension of fibers, and we have proved that just under this condition, your map should be surjective because of you can calculate the image of this map, the dimension of the image of this map, and how to find this element? So simply you have T, you have Cartan subalgebra. So just take the element in T, such that, well, the condition, it is, this element should be sufficiently general. Yes, so this means that the centralizer of this element is equal to the centralizer of the torus T. Yeah? So that is the condition that we need to use. And what is the meaning that you have fixed point? So just T x C sits inside C, xc. So this means that just xc is a fixed point. Of T. So we have to prove that such cosets form the finite set. So we have to prove that such x form the finite set. So x is the cosets, yeah. But let us, yeah, so this means that just T sits inside the conjugate of the normalizer, yeah. But what does it mean? Yeah, so here you have its own torus. Yes, so the Cartan subgroup was the centralizer of the torus, and the conjugate of so this group is just C of the centralizer of G in of X T X inverse. Yeah, so the connected component. So here you have its own maximal torus. But so you see that, yeah, so you see that T is so it is a special element, and it sits in this. So T is the element of this Cartan subgroup. So T centralizes. So T centralizes this maximal torus, and this means that just or in particular, but you see what. So this means that this thing sits in the centralizer of T. Yes, so that means that xt x inverse sits inside the centralizer of the element T inside G, but this is just the centralizer of the whole torus T. So this means that the conjugate torus sits inside Cartan subgroup. Yeah? So this means that xt x inverse sits inside Cartan subgroup. But here, yeah, so in particular you can take the connected component because this is connected. Yeah, so you can put connected component since x t x inverse is connected. And but here, so this is a maximal torus. But there is unique maximal torus in the Cartan subgroup. Yeah, so but here T is unique torus. Maximal torus. So this implies that x T x inverse is just T, and the x is just in the normalizer of. So it means that x normalizes maximal torus. But the normalizer, the connected component of normalizer is equal to connected component of centralizer. Yeah, this is a property of D groups. Yeah. the connected component of normalizer is equal to connected component of centralizer. And centralizer is just a Cartan subgroup. Yeah, so I have written it like this. Yeah, so it is just a Cartan subgroup. So this means that just x, if you take x runs in the coset of n modulo n g t 0, which is equal to c t 0. So that means that, so x runs through the components, so representative of the, so if you take ng and take it modulo this Cartan subgroup, so x, so different values of x modulo this coset are just the connected component of the normalizer. So that means that x runs through modulo, so modulo the coset c g of t 0, x runs through connected components of normalizer. Ага.
У нас там был T, мы хотим для T, да, что?
Да, но мы хотим для T показать, что число x по модулю C, ну, вот таких смежных классов, конечно. Значит, x пробегает как бы, то есть это и представители G по модулю C, но T выбран так, что T, его централизатор совпадает с централизатором Тора. Ну и тут как бы вот он трюк, что я меняю коммутирование, да, что T лежал вот в этом, ну это как бы условие неподвижности, значит T лежал в централизаторе этого дела, но в котором лежит вот эта штука, вот этот Тор. Ну, значит, T коммутировал с этими элементами, в частности с этими. Мы получаем, что, значит, вот эти элементы, они лежат в централизаторе элемента T. Ну, как бы я обратно использую. На централизаторы, то есть тут я использовал централизатор этого множества, а тут как бы использовал централизатор T. Ну, вот это множество лежит в централизаторе T, которое совпадает с централизатором всего T. Но это означает, что вот эта штука, ну, у вас есть две вещи, вот этот Тор и Тор Т внутри централизатора. Но там они должны совпадать, потому что все элементы, они должны быть сопряжены здесь, но они, все элементы, эти элементы оставляют Т неподвижными, поэтому вот эта штука совпадает с этой, а значит x должен принадлежать нормализатору. А теперь я пользуюсь тоже, еще одним фактом, что вот для D-групп, то есть есть теорема жесткости, которая говорит, что связанная компонента нормализатора совпадает со связанной компонентой централизатора. Значит, множество вот этих классов нормализатор T по модулю его связанной компоненты совпадает с нормализатором по модулю картановской просто подгруппы, значит, вот это множество, вот это конечно, вот оно конечно и все. То есть, значит, x, там вы не все можете элементы взять, по крайней мере, значит, x пробегает вот это множество. В смысле, кстати, точнее, все, вы можете, это в частности тоже показывает, что вы можете любой элемент взять отсюда. Да, в смысле, что вот это все множество, это как раз мы его целиком описали. Если вы берете x любой отсюда, то он будет картановскую нормализатор Тора будет нормализовать и его картановскую подалгебру. Поэтому как бы, это в две стороны доказательства. So this proves that this element is special, and this proves this very important claim that which seem to be not very complicated, but I mean a priori, but the proof is quite involved. Да.
So we found T such to put it inside the density theorem.
Yes, to plug inside the density theorem literally.
And this turned out that the density theorem gives
So the density theorem finishes the job. Yeah.
but little t lives inside Cartan subgroup, yeah?
Yes, because it centralizes itself. Yeah. Yeah, so the notice that connected component of the normalizer is the same as connected component of the centralizer for maximal toric. So in more general setting, for any D group, so that is a very special thing as rigidity theorem. So, and now, just now I wanted to say some proposition, but I forgot. Just a second. I wanted to say something and I forget what I wanted to say. So just yeah, so let me also I wanted to say also the following lemma, so which is important for just so the problem that it is rather technical. I mean, I'm not sure that it will be yes, and there was the statement, so that that we still have to prove. So this is the proposition about dimensions. So we have discussed the following, that if you have, we have discussed the tangent spaces of, tangent spaces. So suppose you have the semi-simple element, as was a semi-simple element. And we discussed the following, that so you can consider joint action of S on the Lie algebra. And also you have the orbit, so the orbit in the group normalized by G. You had the orbit that can be put to be consists of the following elements. So it is the set of conjugacy classes. So if H is the subgroup normalized by S, so then this is an orbit. So the translation of the orbit by G inverse inside the H, so it lives inside H. And so here you have, so you want to understand the tangent, so this was called M, so you want to discuss the tangent space of M in the unit element. And in the same time, you have a joint action of S on G, and you have a Lie subalgebra of the elements of G that commutes with S times the complementary subspace. And what we if S is semi-simple, then so in general you have here a joint action. You have here you have the subset of the set of elements that of the Lie algebra that are fixed by S. Yeah, but from the this set, so this action is linear action and it is diagonalizable. And these are fixed vectors by X, so just a joint action by S of Xi is equal to Xi. So this is vectors of eigenvalue 1. So vectors of eigenvalue 1. And you have the following decomposition. So the Lie algebra is decomposed into the direct sum for the operator which is diagonalizable as the set of eigenvalues, and the set of so the set of vectors with eigenvalue 1 is and the other eigenvalues. Yeah? So we have done the calculation that for GLN, this M is precisely the tangent space to the orbit. Yes, so that this is precisely the stabilizer of. This is a Lie algebra of the stabilizer of the element S in G. And we have already considered, so we have proved that M is precisely the tangent space to the orbit. Here I wanted S. Yeah. So tangent space to the orbit, the variety. So here let us call it MH, And if you take the union of all over the element of G, so let us call it Mg. So this is the tangent space to the variety of Mg. Because we have, for G, we have calculation of, so this Lie algebras coincide, and we have proved that the image of differential, so we have calculated the differential of the map that maps G to M. So we have gamma S that maps G to M. G. So here we have calculated that differential of gamma S of G, it is a joint action of S minus 1. And, or maybe 1 minus a joint action. And we have proved just that the image of this differential of gamma S is precisely, so this is a tangent space of Mg, and this is precisely coincide with this set. So the image of this map, so the image of this differential is precisely M, because if you apply, this d of gamma S that maps from G to G, yeah? So this Mg is a subset of G, and here you have a unit. So the tangent space, at least, of, so you may consider gamma S as a map from G to G, but the image with the image of Mg. So this this operator is 1 minus a joint action of S, but on the set, if you write down the set of G as the set of the elements where the eigenvalue is 1 and positive eigenvalue, so if you, so this set maps to 0. So if you write down this d gamma S, so this set will map to 0. So and the restriction to M will be a non-trivial map, because just on each eigenspace. So if you look at this as the sum of the corresponding characters on each eigenspace, the map looks like 1 minus chi, which is so multiplication by 1 minus chi, and this is non-zero element. So this implies that the just tangent space to this orbit coincides with this M. And I claim that just for any H, the Lie algebra of the centralizer of S coincide with the corresponding set of if S, so if you have the following picture, if S also normalize the subgroup H, it also normalizes with its tangent space. Yeah. So just if S normalizes at so normalizes H, it normalizes. So a joint action of S, which is differential of this action by conjugation, it normalizes H, the Lie algebra. So you have the corresponding decomposition. So the algebra of H. So here G decomposes into the elements of eigenvalue 1 plus the remaining elements, and H also decomposes into CH, S plus corresponding M tilde, where these factors are obtained via intersection with H. And I claim that the Lie algebra of CH is equal to the Lie algebra of S. So that was our claim of the theorem. And the argument is as follows. So notice that CH of S. So,
Could you repeat how CH in the algebra is defined?
it is just the set, so you just a joint action of S maps H to itself. Yeah? Okay, and here you have the elements that are fixed by, so the element size that are fixed by H, by a joint action of S.
So for every S, there is their own.
Yeah, for every S, there is their own subset in the Lie algebra, which is Lie algebra on its own. And I claim that this just this centralizer of the centralizer of S inside the Lie algebra is really the Lie algebra of the centralizer H. So I claim that the following, that if you have, so the centralizer is obtained, so the centralizer of S by conjugations in G is obtained by intersection of the centralizer in G and the intersection with H. Yeah? So this means that if you want to write down the Lie algebra, so at least you have evident inclusion into the tangent space. So the tangent space to the variety, so if you have X and Y, the varieties, so the tangent space of the intersection sits inside the intersections of the tangent spaces, yeah? In a point, in the common point, yeah? Okay. So if the Lie algebra is just a tangent space to this group, so the tangent space to this group sits in the intersection of this Lie algebras. So this means, and you know that this is just C G of S. So you know that at least this Lie algebra sits inside this CH. I denote it by this CH. And then I want to get the opposite claim by the dimension reasons. So notice that just note that this MG, MH, the variety that we consider here is the subset of, well, clearly MG, and at the same time it is a subset of H. So this implies that the tangent space of MG in the unit sits inside the MG tangent space of the unit and H, so which is the Lie algebra. And this implies that, so here the tangent space, so this implies that the tangent space of MH sits inside the intersection of M and this H. Yeah, so this H, so that means that it sits in M tilde. So in particular, this means that dimension of tangent space of MH is bigger or equal than dimension of M tilde. But in the same time, this dimension of M, so this is equal to dimension of MH, and the dimension of M is equal to dimension of G, so or dimension of the Lie algebra, minus dimension of the centralizer, so dimension of the centralizer, because this is homogeneous space. So this proves that the following thing, that this proves that dimension of so if I just write this down, this means that dimension of G minus dimension of the centralizer of S, it is bigger or equal than dimension of M tilde, and which is equal to dimension of G minus dimension of G, which is dimension of G minus dimension of this Lie algebra. Yeah? And this implies that, yeah, so since this factors are so equal, yeah, so this implies that dimension of the centralizer is less or equal than dimension of this Lie algebra. Yeah? Just a second. The sign is opposite that I wanted to say. Yeah, so here the dimension was smaller. Yeah, sorry. So this is a tangent space that sits here. Sorry, the dimension is. This implies that the dimension of this tangent space is smaller than this dimension, and this implies that you have this opposite sign. Yeah, and so this on one hand you have inclusion that the Lie algebra has contains is contained in this centralizer, and on the other hand, the dimension of the Lie algebra is equal to dimension of the group, and it is bigger or equal than dimension of this Lie algebra standing here. So this means that they coincide. Yes, so that means that here you have equality. Yes, so that these spaces coincide. So that was the technical part about the tangent spaces to the orbits and comparing the Lie algebra of the centralizer and the set of vectors that just have eigenvalue 1 in the joint action. So maybe it is a good point to stop today. So next time we shall be speaking. So I think it is time to go to reductive group to just to have some theory of invariant theory. So we shall discuss what are quotients, so how to write them down, what are the properties of quotients. And maybe if time permits, I shall tell something more about the structure of reductive groups, but maybe in the end of the course.